Hello, my name is Jeff, and I'll present our ASRU paper, the audiovisual neural syntax acquisition. There is generally two body of work on learning linguistic structure. In the speech community, people are interested in spoken language acquisition, where people look at word or phone segmentation or learning lexical units without supervision. In the NLP community, people are interested in grammar induction, where people learn, where the model tries to induce tree structure directly from text. And more recently, people are interested in using visual modality to guide the grammar induction procedure, like the visually grounded neural syntax learner. Motivated by how babies could acquire language, we observed that there is a gap between these two past research line of work. And this is where our work fits in, where we're interested in learning linguistic structure, such as tree, from speech. So this work is about inducing phrase structure from speech, such that there is no text or ASR needed. We define phrase structure as constituency parse tree, as shown in the visualization below. To this end, we introduce our method, the Audiovisual Neural Syntax Learner, or AVNSL. AVNSL induces constituency parse tree from pairs of image and spoken captions and bypassing text. AVNSL relies heavily on a previous model called the Visually Grounded Neural Syntax Learner. And in a nutshell, AVNSL extends VisionSL to audiovisual inputs. So we'll begin by briefly going over the visually grounded neural syntax learner, or VisionSL. VisionSL induces constituency parse tree from text with the guidance of vision. As shown in the diagram below, VisionSL leverage the image embedding and guide the parser to produces parse tree. The parser takes in a text caption and returns a parse tree. So we're going to focus specifically on how this parser is designed and how the parse structure is induced in this process. VisionSL uses a bottom-up parser. So, for example, for the text caption, a cat is on the lawn. First, there is a scoring module that scores all possible adjacent embeddings and returns an unnormalized score. So it does this for all possible adjacent embeddings. The unnormalized score is then normalized into a probability distribution. According to this probability distribution, we can then sample two adjacent embeddings and combine those adjacent embeddings into a constituents. The representation for the constituents is simply the L2 norm of the input adjacent embeddings. And we can do this procedure bottom-up recursively until we have the final one constituent at the top. And this is how the parse structure is induced. And this discrete sampling process is guided by via reinforce from the text image matching loss. They show that VisionSL performs competitively compared to text-only grammar induction method. It also works on multiple languages. So our method, audiovisual neural syntax learner, essentially adapts VisionSL to speech inputs. At core, we want to extract word-level representation from speech and feed those as input to VisionSL. So we were going to break down this problem into two steps. We're going to first extract word-level segmentation. And then based on those segmentation, we want to extract segment-level representation. And we want to do these two steps without supervision. So I'm going to talk a bit about how on unsupervised word segmentation. So we leverage a recent model called VG Hubert for word segmentation. the idea of VG-Hubert is that word segments naturally emerges from audio-visual retrieval training, as you can see in the visualization below, that it places we've placed attention under visually concrete words very nicely. However, one issue with VG-Hubert, or generally visually grounded word discovery model, is that they typically neglects function words like or the, as these function words are not visually concrete. However, in our case, function words could play a crucial role in defining the phrase structure. So we want to recover those function words. We introduce segment insertion to VG-Hubert. Segment insertion simply places a short segments between, as long as there's a long enough gap between the VG-Hubert word segmentation proposal, as you can see in the visualization below. And in this case, the function words and on are nicely recovered with our segment insertion method compared to the vanilla VG-Hubert segmentation proposal at the top. And here are more examples on how segment insertion heuristic can nicely recover some of the function words. Now, given the word segments, we want to extract the segment level speech representation. And the idea here is that we can obtain the segment level representation by attention weighted over the frame level speech representation. The frame level speech representation can be obtained simply from a speech-only representation like Hubert, or we can take the frame level representation from VG-Hubert. The attention weights can be given by the inherent attention weights from VG-Hubert, or it can be learned jointly with the VisionSL tree sampling module. And by default, we're going to take the frame level representation from VG-Hubert and also the inherent attention from VG-Hubert for getting the word level segment representation. And this segment, so in a nutshell, this is the audio-visual neural syntax learner that induces consistency parse structure from pairs of image and spoken captions and bypassing text. So at the very bottom, we have the speech. We extract a word segmentation and segment level representation without supervision. These segment level representations are then fed into the parser, which is guided by the phrase level audio-visual embedding matching. And this bypasses text or ASR. Now we're going to introduce two additional techniques that improves AVNSL. The first technique is self-training, and previous work in grammar induction has demonstrated that self-training improves unsupervised text parsing. We show that this is also the case for audio-visual neural syntax acquisition. So we begin by training an AVNSL from audio-visual data. We then take the trained AVNSL model and get an initial parse tree. So we have paired speech and parse tree for us to train a supervised parser. And we can train the supervised parser iteratively until the tree F1 score saturated. The second technique is unsupervised decoding. On the high level, we have multiple model checkpoints. And thus, given an input, we can have multiple model outputs. We then define a loss for pairwise model outputs. And the final model outputs is the output that achieved the lowest pairwise loss across all pairwise model outputs. Essentially, we want to take the per sample average output over all possible outputs. So in the case of tree structure induction, given a fixed word segmentation, we can define this loss as negative tree F1 score. So we want to select the tree that has the highest F1 score across all possible model outputs. For word segmentation, where we have multiple word segmentation proposal, we define this loss as the negative of the overlap between two segmentation proposal. Okay, and the implication here is that we train a fully unsupervised tree induction model from speech. And we do this from unsupervised word segmentation, unsupervised tree induction, to unsupervised self-training and unsupervised decoding. Okay, so our experiment is on spoken English and spoken German. We want to first look at the unsupervised word segmentation results on spoken Cocoa. At the bottom here, we see that the segment insertion heuristic we introduced on top of VG Hubert, along with the unsupervised decoding selection, improves VG Hubert for word segmentation F1 score. Noticeably, the recall rate also significantly increases as a lot of the function words are recalled. We're now going to talk about several baselines that we constructed for tree induction. The first baseline is trivial tree structure, where we're given oracle number of word segments, and we can run a right branching binary tree or left branching binary tree algorithm. The second baseline is AV compound PCFG, where we train a compound PCFG on segment level discrete units, where the segments are given from VG Hubert. Another baseline is DPDP compound PCFG, where the difference here is that we take a speech-only word segmentation model as the segment level proposal. The last baseline is Oracle AVNSL, where we train AVNSL with Oracle word segmentations. This is the results on tree induction on English spoken Cocoa. We see that at the bottom here, a fully unsupervised AVNSL outperforms other modeling alternatives. However, because English is inherently right branching, it unfortunately lags behind right branching tree on English. We also show that self-training further improves AVNSL for tree induction. The last table here is on tree induction in German, on German Flickr. And because German is neither right branching nor left branching, we see that AVNSL is very effective here compared to the trivial tree baselines. To conclude our talk, the key takeaway of this work is that it is possible to learn meaningful phrase structure in the form of constituency parse tree from speech without any text or text pre-trained model. The further implication is that we extend both line of research work and language acquisition from speech and multi-model grammar induction. Thank you very much.